Orbital elements are the parameters required to uniquely identify a specific orbit. In celestial mechanics, these elements are generally considered in classical two-body systems, where a Kepler orbit is used. There are many different ways to mathematically describe the same orbit, but certain schemes, each consisting of a set of 6 parameters, are commonly used in astronomy and orbital mechanics. A real orbit changes over time due to gravitational perturbations by other objects and the effects of relativity. A Keplerian orbit is merely an idealized mathematical approximation at a particular time. Keplerian elements. The traditional orbital elements are the 6 Keplerian elements, after Johannes Kepler in his laws of planetary motion. When viewed from an inertial frame, 2 orbiting bodies trace out distinct trajectories. Each of these trajectories has its focus at the common center of mass. When viewed from the non-inertial frame of one body, only the trajectory of the opposite body is apparent. Keplerian elements describe these non-inertial trajectories. An orbit has 2 sets of Keplerian elements depending on which body is used as the point of reference. The reference body is called the primary, the other body is called the secondary. The primary does not necessarily possess more mass than the secondary, and even when the bodies are of equal mass, the orbital elements depend on the choice of the primary. The main 2 elements that define the shape and size of the ellipse: eccentricity, semi-major axis, longitude of the ascending node, horizontally orients the ascending node of the ellipse with respect to the reference frame's vernal point, and finally, argument of periapsis defines the orientation of the ellipse in the orbital plane, as an angle measured from the ascending node to the periapsis. Mean anomaly at epoch. The mean anomaly is a mathematically convenient angle, which varies linearly with time, but which does not correspond to a real geometric angle. It can be converted into the true anomaly, which does represent the real geometric angle in the plane of the ellipse, between periapsis and the position of the orbiting object at any given time. Thus, the true anomaly is shown as the red angle in the diagram, and the mean anomaly is not shown. The angles of inclination, longitude of the ascending node, and argument of periapsis can also be described as the Euler angles defining the orientation of the orbit relative to the reference coordinate system. Note that non-elliptic trajectories also exist, but are not closed, and are thus not orbits. If the eccentricity is greater than 1, the trajectory is a hyperbola. If the eccentricity is equal to 1 and the angular momentum is 0, the trajectory is radial. If the eccentricity is 1 and there is angular momentum, the trajectory is a parabola. Required parameters given an inertial frame of reference on an arbitrary epoch. Exactly 6 parameters are necessary to unambiguously define an arbitrary and unperturbed orbit. This is because the problem contains 6 degrees of freedom. These correspond to the 3 spatial dimensions which define position, plus the velocity in each of these dimensions. These can be described as orbital state vectors, but this is often an inconvenient way to represent an orbit, which is why Keplerian elements are commonly used instead. Sometimes the epoch is considered a 7th orbital parameter, rather than part of the reference frame. If the epoch is defined to be at the moment when one of the elements is 0, the number of unspecified elements is reduced to 5. Alternative parametrizations. Keplerian elements can be obtained from orbital state vectors by manual transformations or with computer software. Other orbital parameters can be computed from the Keplerian elements such as the period, apoapsis, and periapsis. It is common to specify the period instead of the semi-major axis in Keplerian element sets, as each can be computed from the other provided the standard gravitational parameter, gm, is given for the central body. Instead of the mean anomaly at epoch, the mean anomaly, mean longitude, true anomaly, or the eccentric anomaly might be used. Using, for example, the mean anomaly instead of mean anomaly at epoch means that time must be specified as a 7th orbital element. Sometimes it is assumed that mean anomaly is 0 at the epoch, leaving only the 5 other orbital elements to be specified. Different sets of elements are used for various astronomical bodies. The eccentricity, E, and either the semi-major axis, A, or the distance of periapsis, Q, are used to specify the shape and size of an orbit. The angle of the ascending node, omega, the inclination, I, and the argument of periapsis, omega, or the longitude of periapsis, specify the orientation of the orbit in its plane. Either the longitude at epoch, L0, the mean anomaly at epoch, MO, or the time of perihelion passage, T0, are used to specify a known point in the orbit. The choices made depend whether the vernal equinox or the node are used as the primary reference. The semi-major axis is known if the mean motion and the gravitational mass are known. It is also quite common to see either the mean anomaly or the mean longitude expressed directly, without either MO or L0 as intermediary steps, as a polynomial function with respect to time. This method of expression will consolidate the mean motion into the polynomial as one of the coefficients. The appearance will be that L or M are expressed in a more complicated manner, but we will appear to need one few orbital element. Mean motion can also be obscured behind citations of the orbital period p. Euler angle transformations. The angles are the Euler angles characterizing the orientation of the coordinate system from the inertial coordinate frame where is in the equatorial plane of the central body, is in the direction of the vernal equinox, is perpendicular to and with defines the reference plane, is perpendicular to the reference plane, are in the orbital plane and within the direction to the pericenter, is perpendicular to the plane of the orbit, is mutually perpendicular to and then, the transformation from the coordinate frame to the frame with the Euler angles is where the transformation from two Euler angles is, where signifies the polar argument that can be computed with the standard function at and to available in many programming languages. Orbit prediction. Under ideal conditions of a perfectly spherical central body and zero perturbations, all orbital elements except the mean anomaly are constants. The mean anomaly changes linearly with time, scaled by the mean motion. Hence, if at any instant the orbital parameters are, then the elements at time is given by perturbations and elemental variance. Unperturbed, two-body, Newtonian orbits are always conic sections, so the Keplerian elements define an ellipse, parabola, or hyperbola. Real orbits have perturbations, so a given set of Keplerian elements accurately describes an orbit only at the epoch. Evolution of the orbital elements takes place due to the gravitational pull of bodies other than the primary, the non-sphericity of the primary, atmospheric drag, relativistic effects, radiation pressure, electromagnetic forces, and so on. Keplerian elements can often be used to produce useful predictions at times near the epoch. Alternatively, real trajectories can be modeled as a sequence of Keplerian orbits that osculate the real trajectory. They can also be described by the so-called planetary equations, differential equations which come in different forms developed by Lagrange, Gauss, Delaunay, Poincaré, or Hill. Two-line elements. Keplerian elements parameters can be encoded as text in a number of formats. The most common of them is the NASA, NORAD, two-line elements format, originally designed for use with 80-column punched cards, but still in use because it is the most common format, and can be handled easily by all modern data storages as well. Depending on the application and object orbit, the data derived from TLEs older than 30 days can become unreliable. Orbital positions can be calculated from TLEs through the SGP, SGP4, SDP4, SGP8, SDP8 algorithms. Example of a two-line element.